Good afternoon, friends. Today, let's have a discussion on defects in crystalline solids. This is the part one of defects in crystalline solids, where I'm going to discuss about the stoichiometric defects. In the next half, we'll be discussing the non-stoichiometric defects in solids. So, this is one of the very important area where you can get questions in your CET, NEET, as well as your annual examinations. So, you need to concentrate a bit on this topic. All right. So, let's begin. So defects in crystalline solids. Defect basically refers to any kind of an irregularity in the arrangement of constituent particles in the solids or in the crystal. These defects are also called as imperfections in solids. There are basically two types of imperfections or defects. One, it is called as electronic imperfections, which are out of your syllabus, basically refer to the variation in the number of electrons. The next category is atomic imperfection, which can be further classified into point, line or plane imperfection. So in place of imperfection, you can use the word defect. So you can classify the defects of crystalline solids into electronic defects, and the second one, atomic defect, which is further classified into point defect, line defect or plane defect. For your syllabus, you have got only point defect to be discussed. So point defects, a part of atomic imperfections. If the deviation or change occur because of the missing of atoms, displacement of atoms or presence of extra atoms, this is called as a point imperfection. So basically, you can classify the point defects into impurity defect, stoichiometric defect, non-stoichiometric defect. And out of stoichiometric defect, we have got four categories: Schottky defect, Frankel defect, vacancy defect and interstitial defect. And in non-stoichiometric defect, we have got metal excess defect and metal deficient defect. Now coming round to the stoichiometric defects, the defects that do not disturb the ratio of cations and anions are called as stoichiometric defect, which do not disturb the ratio or number of cations and anions. They maintain the electrical neutrality. These stoichiometric defects are also called as intrinsic defect or thermodynamic defect. There are basically four types of thermodynamic defects. 1. Vacancy defect. 2. Interstitial defect. 3. Schottky defect. And the fourth one, Frankel defect. Now what do you mean by vacancy defect? A vacancy defect, when a lattice site is vacant, then the crystal is said to have a vacancy defect. This results in decrease in the density of the substance. You need to concentrate on this area or the question of density. Okay, so in the vacancy defect, the density of the substance decreases. This defect can develop when a substance is heated. So in a vacancy defect, the particles will leave the lattice point and they enter into the atmosphere, or they are left out into the atmosphere. Basically, this type of defect is observed when you are heating a solid. So because there is a loss of constituent particles, the total mass of solid decreases, whereas the volume of solid is constant. We know that density is equal to mass divided by volume. Therefore, as the mass decreases and volume increases, the overall density decreases. Therefore, in a vacancy defect, there is a decrease in density. So now coming round to the interstitial defect. So interstitial defect, basically interstitial site anna nenpitkobeku. Interstitial site is nothing but a void. When some of the constituent particles, maybe atoms or ions or molecules, if they occupy the interstitial site or void, then the crystal is said to have an interstitial defect. This results in the increase in density of the substance. Guys, idನ್ನ ಕರೆಕ್ಟ್ ಆಗಿ ಅರ್ಥ ಮಾಡ್ಕೊಡ್ರಿ. ದಿಸ್ ರಿಸಲ್ಟ್ಸ್ ಇನ್ ಇನ್ಕ್ರೀಸ್ ಇನ್ ಡೆನ್ಸಿಟಿ ಆಫ್ ದಿ ಸಬ್ಸ್ಟೆನ್ಸ್. ಇದೊಂದು ಸ್ವಲ್ಪ ಕ್ವೆಶ್ಚನೇಬಲ್ ಕಾನ್ಸೆಪ್ಟ್ ಆಗ್ತದೆ. ಯಾಕಂದರೆ ಯೂಶ್ವಲಿ ಏನಾಗ್ತದೆ, ದೆರ್ ಇಸ್ ನೋ ಲಾಸ್ ಇನ್ ದಿ ನಂಬರ್ ಆಫ್ ಪಾರ್ಟಿಕಲ್ಸ್. ಸೊ ಮಾಸ್ ಸೇಮ್ ಉಳಿತದೆ. ಆ್ಯಸ್ ಐ ಸೆಡ್, ವಾಲ್ಯೂಮ್ ಇಸ್ ಕಾನ್ಸ್ಟೆಂಟ್, ವಾಲ್ಯೂಮು ಸೇಮ್ ಉಳಿತು. ಡೆನ್ಸಿಟಿ ಕಾನ್ಸ್ಟೆಂಟ್ ಬರಬೇಕಾಗಿತ್ತು, ಬಟ್ ಇಲ್ಲಿ ಏನಾಗ್ತದೆ, ಡೆನ್ಸಿಟಿ ಇನ್ಕ್ರೀಸಸ್. ಯಾಕೆ ಅಂತಂದರೆ, when the particles move into the void, they basically shrink the substance. So because of the shrinkage, there is a slight decrease in the overall volume of the substance, whereas mass is constant. So density is equal to mass divided by volume. Because the denominator is decreasing, that's why the overall density is increasing. So let's have a look. So in this particular diagram where I'm marking it off, there is a loss of constituent particle, therefore we call it as a vacancy defect, and in the other part we have got the particle which has occupied the void, and we call it as an interstitial defect or interstitial impurity present. The next category of defect, that is Schottky and Frankel defect, are most commonly observed in ionic solids. Guys, ಇಲ್ಲಿ ಇನ್ನೊಂದು ಪಾಯಿಂಟ್ ನೆನಪಿಟ್ಕೊಡ್ರಿ, vacancy and interstitial defects are common in non-ionic solids. It may be common in molecular, in case of covalent solids, metallic solids, etc. But when we come round to the ionic compounds, the most common stoichiometric defect are Schottky and Frankel defect. So what happens in a Schottky defect? Alright, in an ionic crystal, say of the type AB, where A carrying a uni-positive charge A plus and B carrying a uni-negative charge B minus, equal number of anions and cations if they are missing from their lattice site. Equal number of anions and cations missing from their lattice site, so that the electrical neutrality is maintained, stoichiometry is maintained. We call the defect to be Schottky defect. This type of defect is observed in ionic compounds that have got high coordination number. Guys, ಇಲ್ಲಿ high coordination number ಅಂತಂದಾಗ, for your reference ನೀವು ನೆನಪಿಟ್ಕೊಡ್ರಿ, group 1 elements are preferably having a very high coordination number. So group 1 halides ಏನಿದಾವೆ, they usually show a Schottky defect. There should be a small difference in the size of cation and anion. Difference in size of cation and anion ಏನಿರಬೇಕು, ಕಡಿಮೆ. So extreme left ಅಲ್ಲಿ ಇದ್ದಿದ್ದು elements and extreme right ಅಲ್ಲಿ ಇದ್ದಿದ್ದು elements, when they combine, the elements which are at the extreme left of the periodic table and at the extreme right of the periodic table, when they combine, such ionic compounds will exhibit Schottky defect. Examples should be NaCl, KCl, KBr, cesium chloride, etc. So density ಏನಾಗಬೇಕು? Quite a simple logic, because the particles are lost, mass decreases, that's why density decreases. Now coming round to the Frankel defect, if an ion, preferably an cation, ಯಾಕಂದರೆ cation size ಏನಿರ್ತದೆ ಸ್ಮಾಲ್ ಇರ್ತದೆ, anion size ಏನಿರ್ತದೆ ಲಾರ್ಜ್ ಇರ್ತದೆ. If an ion is missing from its lattice point and if it has occupied the hole, okay, or a void or an interstitial site, that kind of a stoichiometric defect is called as Frankel defect. Okay, since the cations are usually smaller than the anions in general, that's why the cations leave their lattice point and they enter into the interstitial site, creating a vacancy at the lattice point and an excess element or an excess ion in the interstitial site. This type of a defect is present in ionic compound which have got low coordination number. Guys, illi transition metal elements anna ನೆನಪಿಟ್ಕೊಳ್ಳ್ರಿ, higher transition elements preferably, these have got low coordination number. There should be a large difference in the size of anion and cation. The compounds that have high polarizing cation and easily polarizable anion, ಅದೇ ನಾನು ಅಂದಿದ್ದ example transition metals ಇಂದು. Example would be AgCl, AgBr, AgI, ZnS, etc. The density of the solid remains constant. ಇಲ್ಲಿ ಯಾಕೆ ಅಂತಂದರೆ, the cation is so small that it will not undergo any kind of an attraction or repulsion when it enters into the void. That's why the overall volume remains intact or constant. Hence, in case of a Frankel defect, there is no change in density. So here I have got a diagram. See, look at the size of the cation and look at the size of the anion in a Schottky defect. A cation is lost and an anion is lost. Now if you observe over here at this point, okay, the cation is left and it has occupied the point over here in the void. So this is about the stoichiometric defect. So once you come back to the college, I'll be waiting with open arms to discuss it in detail. Thank you.